this part, we are going to discuss about the thermal properties. We'll just be giving you a very brief intro about what happens when an externally applied heat is applied to any particular substance. As a result, what is the influence that it produces on the dimensions of the substance. So this is what we are going to discuss in this part, wherein we try to understand about the relationship between the thermal variation of the length with temperature, and how much is the variation, how much is the force that is produced, or analogous of the force that is produced as a result. We'll try to understand about that. So hello guys, so before we go on to discussing some problems on this based on the past year papers, let's try to do some understanding about the thermal expansion. So what basically does thermal expansion actually stand for? So if we talk about thermal expansion, first of all, let's say that many of you would have traveled by train. Yeah. So in trains, if you have ever observed that the tracks on which the trains move have basically bolts which are tied up, right? And in many other circumstances, if you just have a look at some things like a metal bolt tied to something, or let's say stuck to something, there is always going to be some gap that is kept. During summers, you will see that there is a gap. During winters, you will not get to see that gap. Why does that happen? Basically, that happens because of what is known as thermal expansion. That is, due to heat, there is going to be a change in the length or the change in area that takes place, right? So let's try to understand more on it. So for instance, you say that you have a rectangular sheet of metal which has a circular hole. So this is not looking like circular, but let's assume that it is circular. So what happens to the size of the hole when the metal is heated? So if we heat the metal, then what exactly is the happen? It gets larger, it gets smaller, it stays the same. So obviously the last two cannot be possible because when heated, obviously the metal kind of, let's try to understand it this way. We are talking about the hole. So when the metal is heated, obviously the metal will try to expand everywhere. The metal sees an opening in the middle. So obviously the metal will try to expand. So when the metal expands, what happens? The size of the hole is going to go down, right? But there is another way to look at it as well. If you can somehow restrict the size, then the metal is going to go further away, right? So there is a possibility that because you have a hole in the metal, so that hole in the metal is going to stay or become smaller because of an increase in the temperature, right? Now let's try to understand it in a more detailed way. We know that in a metal, there are microscopic spacings where the metals are actually arranged in a proper definite order. There is a proper definite shape and the proper definite order that keeps the metal atoms intact. Now what is going to happen when you increase the temperature? These metal atoms will start vibrating. They will start oscillating about their main position. So as the temperature increases, the amount of vibration, amount of oscillation is going to increase. And so the spacing between consecutive elements or consecutive atoms is also going to increase, so with temperature. So if I just talk about, so you have a regular arrangement out here, and on increasing the temperature, the arrangement looks somewhat like this. So this is what you get. Now how exactly does this take place? So let's try to understand it. So we talk about what is known as the change in volume taking place. So when you are heating it, obviously there is going to be a change in a length, there is going to be a change in area, there is also going to be a change in volume. All these things are possible. So how exactly do we understand? We say that the volume of the matter expands when the atomic spacing actually increases, right? So the volume is going to expand. It's going to, so if I say this was the original volume, so finally this is the new volume. This is the new volume. So when this has done, so effectively because of a change in temperature by an amount delta T, increase in temperature, the volume also changes by a factor delta V. So an increase in temperature actually increases the volume. So you get what? You get the delta V, which is equals to some proportionality constant of temperature. So beta V naught is the original volume into delta T. So this is the change in volume that takes place. So a volume increase is the same as a density increase, because look at it in a very simple way. You're not changing the mass, right? So if you're not changing the mass, volume has increased, so mass per unit volume is going to decrease, correct? Because the density, so that is mass per unit volume, that is going to decrease because your volume has increased, right? So this is how exactly it works. So going further, so for small volume changes, if I say, so for small volume changes, the relationship between volume and temperature is linear. We are not talking about huge temperature changes. So if the temperature change is large, obviously their higher order corrections are going to play a role. But if we say that the volume and temperature for the change in temperature, let's say delta T, small, quite small, so in that case delta T square and delta T cube, these are going to be negligible, right? So if these are negligible, what happens as a result? You only say that the change in volume is going to be proportional to change in temperature, and this coefficient is known as beta. So beta is nothing but the volumetric coefficient of expansion. So delta V is the change in volume, which is going to depend upon how much was the original volume. So larger is the original volume, more is going to be the change in volume possible. So delta V is equals to beta V naught delta T. So these are some of the values, just for your information, of beta. So quartz has 1 into 10 to the minus 6, Pyrex has 9 into 10 to the minus 6, and so on. And air has something like 3400 into 10 to the minus 6. So this can get expanded so much, right? Okay. Now if we take a question, let's say you have a 72 liter steel gas tank which is open and filled to the top with gasoline or petrol. Beta is given as 950 into 10 to the minus 6 at 18 degrees centigrade. The car sits in the sun and reaches a temperature of 32 degrees centigrade. Okay, so how much gasoline actually overflows from the tank? So what we need to understand, how much is the volumetric expansion that has taken place because of the change in temperature. So if we have to do it, so we'll say that delta V is going to be equal to beta V dot delta T. So beta is given to us, original volume is given to us, the change in temperature between 18 and 32 is 14 degrees centigrade. So that results into a change in volume of 0.95 liters. Since the tank expansion was small, you will get more gas if you fill it when it's cool, right? So what you do is basically, if you are in a cold temperature, then you can fill in more gas because there is more space that is left and the gas does not expand much, right? But if you are in something like very hot, you will not be able to fill in much more fuel, right? Okay, now let's go further and talk about for the case of water. So we know that most of the substances expand uniformly with temperature, but water is kind of it has an anomalous behavior. So it basically, it is below 4 degrees centigrade, the water is going to expand as it kind of cools down. So you know that why exactly it happens. You would have studied in chemistry about something known as hydrogen bonding. So because of hydrogen bonding, there are individual water molecules which get arranged in a structured way, but because of arranging in a structured way, there are hydrogen bonds that come into the play. Hydrogen bonds have a very less strength as compared to the normal covalent bonds, and because of that their bond length is more. So because their bond length is more, they prepare a structured kind of a cubic structure of ice, but that has a very less density because for the same mass the volume occupied is small. So below 4 degrees centigrade the water expands and forms ice. So between 4 degrees centigrade and 0 degrees centigrade actually the water expands. If you talk about in reverse, so the volume, if we talk about starting from 0 degrees centigrade going further, from 0 degrees centigrade to 4 degrees centigrade, first of all the volume decreases and then it follows the normal rule, that is the volume starts increasing then. Okay, very cold water stays on the top and hot water comes down. Ice is even less dense as compared to normal water, that we have just understood. Okay, so there were some peculiar things about water, just for your information. When we talk about solids we know that they have a particular dimension and therefore their way of expanding is different as compared to liquids or gases. In this case, the dimension is going to matter the most. So if I say that you are increasing the temperature, so if you are increasing the temperature by a factor delta T, the length is going to increase by a factor delta L, right? So there is going to be a focus on one dimensions. You can also have simultaneous focus on multiple dimensions as well. Other dimensions are also going to be present. For instance, let's say you take a rod, okay, and you heat it. So if you heat it, basically what's going to happen as a result, when you are heating it, the expansion is going to take place along this direction, right? But there is not going to be much expansion taking place here. So what we'll be talking about the length, about on the length side, what is the dimension that is getting affected the most. So that is what is known as the stretching the solids. So let's try to understand it more. We know that a volume can be represented as the length, height and width. So if I just say that this is a kind of cuboid surface that I have, having all the sides different. So let's say this is my length, this is my width and this is my height. So I have the three sides. So if I say L0, W0, H0, so these are the three dimensions that I have. So because of the change in volume, I will have what? Delta L, H0, W0 remains constant. Then if there is a change in height, then L0, W0 remains constant. If there is a change in width, L0 and H0 remains constant. So these are the things. So as a result, we'll get the change in the volume taking place. Correct? Now further, if I say that the change is the same along all possible directions, what you can simply put in as delta V can be represented as delta T, that is the temperature change that is being constant, beta by 3. First of all, when there is a change in the length, so you write it in terms of L0, then you write down in terms of H0, and then you write down in terms of W0. As a result, if you combine all of them, you will see that delta L can simply be given by, because when we talked about initially it was for the case of volume, so for volume we define it in terms of beta, for length let's define it in terms of alpha. So the coefficient of linear expansion of solids, linear expansion is alpha. So if you write down in terms of alpha, so we find that alpha is nothing but beta divided by 3. Okay, so the linear coefficient of expansion is related to the volumetric coefficient of expansion by a factor of 3, or we can also reverse it and say that beta is equal to 3 times of alpha. Okay, let's try to do some problem on it. So we have the steel bed of a suspension bridge is 200 meter long at 20 degrees centigrade. If the temperature goes from 30 degrees centigrade to 40 degrees centigrade, what is the contraction and expansion that is possible? You see that it has a length of 200 meter at 20 degrees centigrade. So now what you need to find out is that how much is the contraction or expansion that is possible. So if we talk about the case of linear expansion, we will say that delta L is going to be equal to alpha L0 delta T. Alpha is the linear coefficient of expansion, L0 is the original length that it had, and the temperature is actually this difference minus 50. So if we talk about, okay, so there is one difference, so this should be minus 30 degrees centigrade. So from 20 degrees centigrade to the minus 30 degrees centigrade, the difference in temperature is minus 50, right? As a result, we have the minus 50 here. So in this case, there is a contraction that's going to take place. In the case of summers, it goes from 20 to 40. So you will have the temperature change as 20 degrees centigrade. So the length change becomes 0.048 meters. So this is what we talk about the linear coefficient of expansion. Fine. Okay. Now let's come to the point when we talk about the thermal stress. This is the last point here. So thermal stress we have talked about in the case of linear coefficient of expansion, volumetric coefficient of expansion and so on. Now if we talk about the thermal stress. So in the case of thermal stress, we know that F by A for linear coefficient of expansion is for tensile stress, if you say. So this is defined as delta L divided by original length L0. Temperature change, we know that the change in length is equal to delta T into alpha L0. Here we did not specify what was the reason for the temperature change. Now if I say that what was the reason for length change, now if we are specifying that temperature is the reason for length change, so if you just substitute it here, so you'll get F by A as equals to alpha Y delta T. So that is how the force and the area are related to the change in temperature and the Young's modulus. Yeah. So hopefully you understood whatever we discussed. We'll continue further with the problems on this particular topic. In this part, we got to know about how the length varies and similarly the dimensions vary when we basically change the temperature. Generally, an increase in temperature results into an increase in length and similarly change in the volume. In the same way, if you talk about in the bulk way, in that case an increase in temperature effectively changes the bulk modulus, or it effectively changes the volume of the whole substance. Vice versa, an increase in temperature results into a decrease in pressure, or an increase in pressure results into a decrease in temperature. So these are the things that we got to know in this particular part. Now, on the whole, we have understood how the length varies as a function of force and temperature. So now let's try to discuss about some problems in our next part.